Okay, so tomorrow is going to be the first meeting with project advisors. You guys should all know who your project advisors are now, either through a Piazza posting or an email. Brian D'Alessandro, he's actually out of town, so he's going to be making individual appointments via Skype or video chat or something. So hopefully there's some communication going on between those groups and Brian. And of course, Chen is not in the country, so you'll be doing video chat with him. But the other three advisors are here, and you'll meet with them tomorrow. It'll be like a 5-minute pitch of your idea. You'll get immediate feedback. If you have to leave at 8, kind of let people know in case there's any overage, so you can go first. All right, so that's all to say about the projects tomorrow. And so let's talk about what we're talking about today, which is ensemble methods. The main highlights for today will be random forests, and we might start into some add-a-boost, a boosting technique. But along the way, we're going to talk about some statistical technique called the Bootstrap, which motivates motivates bagging and, in fact, random forests that we'll talk about. OK. So we'll start with a review of bias and variance. First of all, what's a parameter? We're in our statistics framework now, statistics vocabulary. And a parameter is a function of a distribution. So we have a probability distribution P. We would like to estimate some characteristic of the distribution. What are characteristics of distributions that we know? Yeah, mean, variance, median, kurtosis, quantiles. Okay. The entire distribution itself could be a parameter. It's still a function of the distribution. OK. So these things are called parameters. We can denote them as mu equals mu of p to show that mu is a function that operates on the distribution itself. And a lot of statistics is about estimating parameters. All right, so what's a statistic? Well, as you expect in statistics, we always have this data set, right? That D, so we have a sample, say IID, from the distribution P. A statistic is just a function of the data. So the statistic S is any function of our data sample. All right. A statistic gets a special name if its purpose is to estimate a parameter. And we say a statistic is a point estimator, a statistic mu hat, say, which is a function of the data, is a point estimator of mu, which is a function of the distribution generating the data, if mu hat is approximately equal to mu. But more or less, if we intend mu hat as an estimator of mu, then we say it's a point estimator of mu. Just a little bit of very general terminology for you guys. OK. So suppose we have a real valued parameter. So most of the things we mentioned were real valued. The mean, standard deviation, these are all numbers, real values. They don't have to be. A parameter could be more than just a real value. It could be a function itself. Could be a pair of numbers. Anyway, but in this case, real valued parameter. And mu hat is our real valued estimator of mu. And when we have real valued estimators and parameters, we could do things like talk about bias and variance. So we define the bias of mu hat, this you guys should know, to be the difference between the expected value of the estimator and the true value of the parameter. Does this make some sense? So the expectation of mu hat somehow depends on mu in some way, right? Mu is part of the probability distribution that we're using when we compute that expectation. So these things, the expectation is where mu comes in, and expectation of mu hat equals mu. Then we're in a situation called unbiased, so zero bias. All right, and the variance of mu hat is just the variance of the estimator, definition of variance. OK. Unbiased is if bias is 0. So here's a point I wanted to make. It's that neither the bias nor the variance depends on a specific data sample. It's not like we sample n points IID from probability distribution, and we say, well, what's the bias on this data set? What's the variance? No. The bias and the variance depend on what the function is, mu hat, the statistic, what's the actual function for the point estimator, and what's the distribution, p. So, and that comes through because in the bias and the variance, there's no direct reference to dn. We're taking the expectation over the data set. All right, so the expectation is random, rather the data set's random, and we're taking the expectation over the data set, which is kind of as though, well, we'll see what that's like in the next slide when we talk about how we estimate it. All right, so how do we estimate the variance of mu hat? You see it has this expectation of mu hat and expectation of mu hat squared in it. So let's get estimates of those things, and we just subtract them, and then we get the variance. All right? OK, so what do we usually do? What did we do back in risk when we wanted to estimate the empirical risk? It was the expected loss, right? So we had this expectation, and we need to compute it with respect to some probability distribution, but we didn't know the probability distribution. So we had a trick, right? It's not a trick. It's just what happens in statistics.
Law of large numbers.
Yeah, OK. So law of large numbers. So we didn't have the distribution, but we have a sample from the distribution. So we were calling it D. So here, dn, sample of size n. And now let's just take the empirical average over a bunch of things and say that will estimate the expectation. OK, so let's see how to apply that reasoning here. So instead of a single sample dn, let's suppose we actually have b independent samples of size n. So we have the probability generating distribution. We draw a sample of size n and call that d1 sub n. And another one, call that d2. Let's grab b of them. OK? And what we'd want is, so expectation of mu hat is the expectation of what would happen for mu hat for randomly chosen d. But we'll estimate it by taking b randomly chosen data sets and averaging. All right, so what's that look like? Expectation of mu hat is approximately equal to the average over b data sets of mu hat on that data set. Is that clear? So how many elements are in d sub n superscript I? What is that? Yeah, this di sub n, that itself is a sample of size n from the distribution. And we have b of those samples. All right. OK. Good. So that's how we can estimate, in some hypothetical world where we got b repeated samples from this distribution, that we can estimate expectation of mu hat. And similarly, we could do mu hat squared. Fine. And we get this formula to estimate the variance of mu hat. So what good is estimating the variance of our estimator? Why is this interesting to statisticians or anybody? So there's some mu that we want to estimate. We have this point estimator, this formula for point estimator, which says, you give me some data, and I'll tell you how to come up with an estimate of mu. And that's mu hat of the data. So why are we interested in this variance of mu hat? Yeah, if we want to know something like the confidence interval. So it's not just, yes, mu hat is a point estimator, but sometimes we want what's called an interval estimator or a confidence interval, where we don't just say mu hat, we give some range, like, yeah, it's mu hat plus or minus 5%, plus or minus whatever. So it's the plus or minus that's giving the range to get some handle on that. That's why we're interested in the variance. So what would the plus or minus be, roughly, in terms of variance of mu hat? So it should be mu hat plus or minus. OK, so 1.96 or something times what? Standard deviation of mu hat, which is what in terms? Is a square root of the variance. OK. So the variance of mu hat isn't quite the units that we're looking at. We need the standard deviation of mu hat, which is square root of variance. OK. All right. Like that. All right. OK, so we had this estimator mu hat, and we talked a little bit about how we might be able to come up with the variance of mu hat in some way. What if we wanted to understand the whole distribution of some estimator mu hat? Okay. So how might we do that? All right. So suppose we grabbed, in this picture, what's happening is we're grabbing 1,000 data sets of size 100. All right? So you get a data set of size 100, that's one of them. And we do that 1,000 times. And for every data set, we estimate this point estimator, now alpha hat. Okay, it's alpha hat now. And alpha hat has a value for that particular data set. The data sets are all generated by the same probability distribution. All right? So alpha that we're trying to estimate, alpha of p, the parameter we're trying to estimate for the probability distribution, that's the same every time. And because the data set we sample is random, alpha hat will be a little bit different every time. And we can plot a histogram of all the alpha hats we get from all the different samples. So this is what this histogram is showing. The pink, that line in the middle, purple, is that's the true value of alpha. And then we see that alpha hat has some spread around the true value. OK. So how could we, if we had this, can we estimate the standard deviation? Yeah, it's about that. But the point is that this has more information than just the standard deviation or the variance. This is an estimate of the entire distribution of alpha hat. Okay. All right. So this was all well and good. We are going along this path of having repeated samples of size n. But in real life, we usually get one sample of size n. So, and if we wanted to get variance estimate, we could, for example, take our sample of size n and divide it up into into B groups, right? And then kind of get an estimator on each of the groups and then get the variance. But the problem with that is, what's the problem with that? If we break this data set n into, well, if we take the sample of size n and we break it up into groups, that they each should be independent. That's fine. The issue is that the individual groups are small, and we would get a better estimate if we could use the whole thing of size n all at once. So if we use it all at once, we don't have an obvious way to get variance. If we break it into small groups, we can get an estimate and a variance, but the estimate's based on a very small group. So that doesn't sound so great. So the question is, can we get the best of both worlds somehow? You get an estimate from the entire data set of size n and have some estimate of its variance. Yeah. OK. OK. So the bootstrap, that's the motivation for the bootstrap.
I have a question.
Sure.
For the slides with the
Yeah. OK, great question. So what happens, so all these, every point underlying this histogram was the value of alpha hat based on a sample of size 100. So the question is, what happens if that sample were of size 10,000? I like that question a lot. What happens to this, what does this histogram look like in that case? OK, so it gets narrower. It gets, so like the variance, the standard deviation of this distribution gets narrower. Yes. Right. Why? What's happening there?
Make a better estimate?
Yeah, the estimates are getting better. The estimates are converging to the value that to their expectation. Hopefully, that's consistency. Yeah. Any other questions?
So in this case, how can we say this? What is the standard deviation using the bootstrap? So you have to define a number of
Yeah, so this is every sample is of size 100. If you want to, your original data set was of size 100. You have your estimate, you have your point estimate for that data set, alpha hat of 100. And now you want to know, what's the variance of this thing? Okay, now to do that, you imagine that you take a lot more samples of size 100, and then you look at the variance of those. Does that answer your question, or?
No, I mean, like, if I have a sample size of like 10,000, and then I do Bootstrap, each of the data set is of size 100.
No,
And
you said 10,000.
no, I said 10,000 random data sets of
Okay,
size.
so Bootstrap of size 10,000.
No, yeah, I mean, like
10,000, B equals 10,000.
Yes, B equals 10.
Okay.
So like I use 10,000 and he used like 100,000.
Yeah.
So we will have different result of the standard deviation.
Okay.
Right.
No. What happens, so this thing gets narrower when n gets larger. So this 100 is replaced by 10,000. What happens when
The B is
B gets larger? We have more Bootstrap resamples. What do you guys think happens then to this histogram? Say again? Yes. Same but more smooth. So the distribution of alpha hat based on a sample of size 100, that has nothing to do, that's just a distribution. We're estimating that distribution by taking lots of data sets of the same size. The more data sets of the same size that we take, the better our estimate of that distribution becomes. So yeah, we could, if we had a lot larger B, we could probably make these bins a lot smaller and it would be nice and smooth. That's what happens. Okay, good question. Okay, so the Bootstrap. So first let me define a Bootstrap sample. A Bootstrap sample from a data set, Dn, is a sample of the same size, size n, drawn from Dn with replacement. Okay? So picture, a bucket of all the samples that you got in your initial data set, in your initial sample of size n. And then you reach in and you grab one, and you record it, and then you put it back. And you reach in again, and you grab a random one, and record it, and put it back. And you do that n times. And that gives you what's called a Bootstrap sample from the original sample. Okay. So some interesting things are going to happen with a Bootstrap sample because we're sampling with replacement. So we're going to have repetitions, right? We're also going to have items in the original sample that never get pulled out in our resample. Right? We can calculate the probability of that. So let's do that. So every item in the original sample, every time we reach in to grab it, there's what's the probability that we don't get it? 1 minus 1 over n, yeah, right. And every time we reach in and grab it, it's an independent event. So the probability that we never grab it in n tries is 1 minus 1 over n raised to the nth power. Good. And what is that? Yeah, close. Yeah, exactly. That's right. As n goes to infinity, this converges to 1 over e, which is roughly a third. Exactly. So so the probability of, the expected fraction of balls that are left behind is about a third in every Bootstrap sample. So there's definitely some diversity in these Bootstrap samples. Every time we go for it, we're getting, maybe about 70% overlap or something, but not complete overlap. All right. So that's Bootstrap. This is a quick picture of it, although I think it's pretty clear. If the original data set is on the left, data set of size 3 observations of x and y. The first Bootstrap sample has the third observation repeated twice, and the second one's missing altogether. The second Bootstrap sample has all of them, so that's exactly the same. And the last one has 2 repeated, 3 is missing. So that's B equals 3 Bootstrap samples, yes?
So why the sample size be the same as the original?
So why are we choosing a sample size the same as the original data? Well, I think the motivation is pretty clear in the previous discussion. because here we had a fixed data set size. It was of size 100. And we wanted to know what's the performance of alpha hat on a data set of size 100. And so what we did was we drew a bunch of data sets of size 100 from the original distribution. Okay. Basically, the fact that they're the same size follows from this whole discussion. Whereas now, instead of here, we are saying that we're drawing from the data sets from the original distribution. Instead of that, we're saying, well, we can't actually do that. So what we're going to do is take bootstrap samples from the sample distribution. Is anyone else puzzled by this? Why there's an equivalence? Why it makes sense to be talking about bootstrap samples that are the same size as the original sample? Yeah.
Are you basically like maintaining the probability distribution by doing it with replacement but still taking a sample of size n? Is that the point?
We want to have
Back, so now you still have the same probability of drawing that or something else. Is that like the point of putting it back but still taking it of size n?
Okay. So first, why do we want it of size n? First, let's assume we wanted it to be of size n. You need to put it back or you're going to get the exact same thing every time. If you don't replace it, you're just going to get the whole, it's not a different sample. It's the same as the original data set.
No, I get that.
Okay, so then the question is, why is it of size n?
I guess. What I'm saying is like that's why you're kind of combining replacement and size n to try to get like the right distribution.
Yeah, we want of size n, but we want a little bit of diversity because we want to pretend that the bootstrap sample is kind of like taking a fresh sample from the probability distribution, even though it's really a bootstrap sample from the sample. So yes, it's kind of like simulating. We would like to imagine that the bootstrap sample is a rough approximation to a fresh sample from the original distribution of size n. That's the objective, which seems not entirely convincing that that would work. Maybe plausible, yeah.
It's not more efficient if you use linear probability distribution and you reach a random number based on this probability distribution and take it from this distribution instead to use this method?
You're saying is it more efficient
Yes.
than to generate a sample from the original distribution?
No, it's more efficient if you generate your distribution, you take your data, you fit your distribution, then you generate random numbers based on that distribution that you fit it.
Oh, okay, that's interesting. So that's actually, if I understand correctly, you're saying you take your sample, and then you have a model, and you fit your model to the sample. And then you draw data from the model,
Yes.
random. Yeah, that has a name. That's called a parametric bootstrap. That's interesting. Okay, but that's something different. Yeah, but that's a real thing. Okay. All right. So bootstrap method, I kind of alluded to it. A bootstrap method is when you simulate having B independent samples from the distribution P by using B bootstrap samples from the sample Dn. Okay? So the entire first section of this lecture was, if only we had B independent samples from the probability distribution, we could do this cool stuff like estimate the variance of our estimators. And then we said, but we don't really have B independent samples. And a bootstrap method is saying that might be okay. Why don't you just take B bootstrap samples from your original distribution and treat them as though they were independent samples from the original distribution? All right, so we have our original data Dn. We make B bootstrap samples. I've written not script D here, just regular D to kind of say bootstrap. And so then for each bootstrap sample, we compute some functions, this would be a statistic. And we work with those as though they were drawn IID from P. So the amazing thing is that this often comes pretty close to what you would get with actual fresh samples of size P from the original data generating distribution. That this works is, I find it surprising. The justification is both empirical by running experiments and theoretical with some fairly heavy mathematics, which we're not going to get into. But it's as a practical tool, it's quite effective. So here's an illustration. So I'm going to repeat what we had before. We had the histogram. Before the histogram, so here's the histogram. On the left is the histogram we had originally. That's where we had 1,000 independent samples of size 100 drawn from the original distribution. That's this guy. The middle histogram is, instead of 1,000 real independent samples, we're taking 1,000 bootstrap samples from our original sample of size 100. And we histogram those estimators up, and we get this histogram in blue, which to my eye looks pretty close. Pretty close. On the right, we have another view of the data. The box, what's that called? Box, stem and leaf? Stem, anyway, yeah, box plot. All right. So this is our illustration of the effectiveness of Bootstrap. You can take some statistics if you want to go deeper. Yes?
I have a question. Here, you can estimate the, you can calculate the estimator based on the real data set based on the size of the real data set is n, right?
Yes, the size of the real data set is n.
Yeah, and you do the bootstrap method, and you estimate based on the data set, the data set with size of n for b times.
Yes, we take B bootstrap
Yeah.
samples of size n, yes.
So why you do this? Because they both calculate based on the size of the data set.
Yes, everything is calculated based on a data set of size n, that's right.
And you calculate only once based on the real data set, and you calculate b times on Bootstrap method.
That's right, we can calculate once on the original data set, and we do the same thing B more times on each of the bootstrap.
Yeah,
That's
why
right.
don't you just calculate the real data set for only once directly?
So the question is, you already got, say, mu hat on the original data set. Why did I just calculate it B more times on the bootstrap data sets?
Yeah, that's my question.
Anybody have an answer? That was a lot of answers. What?
You won't have an histogram, you will have just one value.
Say again?
You won't have an histogram, you will have just one value.
Yeah, so for example, the first motivation was we have this estimator, mu hat, based on the data set, but we want to put error bars on it. We want to know how much variability there is. Maybe we got another data set and it's a different number. And we want to be able to say, it's very common to, when you give an estimate, to say, oh, this is, the temperature today was right now is 80 degrees plus or minus a half a degree. Not a great example, but when you do a poll or a sample or something, you have an error range on your estimate. But we don't have a way to get an error range. We don't have an obvious way to get an error range if you just take mu hat of your data set. What else can you do? If you did mu hat of B copies of that data set, well, then you can look at the actual spread of those estimates to get an estimate of the standard deviation of your original estimate.
Yeah, so it's just like you generate B more data sets based on the real data sets.
Yes.
So you train B times, so you get better outcome, right? Just like you train B different data sets, right? Am I right?
So I'm not sure. You said I trained B, I got B separate estimates, and so it's better? What would make it better? Maybe if you average them together? That might make it better. The reason we're doing B separate ones is because we want to get an estimate for how much things vary from data set to data set. That's why. It's not about making it better yet. It's about estimating how variable it is. Okay. Yeah?
The reason I wanted to have n was what?
N.
Like we wanted to have each sample generation, we wanted to have n the number n stay the same.
That's right.
The reason is that we're going to estimate the variance. The variance might change if you have different n's, or what's
Yes.
Yeah.
Well, yes. Okay. All right, suppose we have a probability distribution of mean mu. We draw, say it has standard deviation 1. All right, so we draw a sample of size n from normal mu1. We want to estimate mu. We don't know what it is. OK, so what's a good estimator? All right, mu hat of our data. OK. OK, what's the variance of mu hat? Woo! You guys know? All right, I'll write it down as you guys go. 1 over n squared. Variance of a constant times a variable is the square of the constant times the variance of the variable. Great. Now we get to the summation. What happens with the variance with the sum? We can move the variance inside the sum when? When the xi's are independent, great, uncorrelated, or sufficient. So we can write 1 over n squared sum variance of xi. What's the variance of xi? Great. All right, so this is 1. We're summing 1 to n of 1. What's that?
1 over n.
And then the final thing is?
1 over n.
All right, good. So the variance of mu hat is 1 over n. So that's the dependence on n. Great. So now, so by mathematics, we just figured out that the variance of mu hat is 1 over n. The problem is, a lot of times you come across an estimator that we cannot do that calculation. We do not know how to figure out what the variance is. We don't know how to do the math to calculate it in closed form, what the variance is. So the bootstrap is a way to figure out what that variance is. But the reason I wrote that out here is because, yes, so the distribution of mu hat. And what do I mean by the distribution of mu hat now? What I mean is every time you take a sample, you get a mu hat. And then you take another random sample of size n, and you get another mu hat. And then you histogram those up. OK. And then standard deviation would be what, roughly, for this histogram? 1 on square root of n, yeah. OK. So as n gets bigger, this thing gets really small. And so, yeah, for, this might be n equals 100, and n equals 1,000 might look. OK. So as we change n, the shape of the distribution we're estimating changes. So we're estimating this distribution by getting sample points, right? And we have to be drawing those sample points from the same distribution, which means they have to be estimators using data sets of the same size. That's what's going on. OK. Does that help? Yeah. Oh, great.
So basically, Bootstrap is a method for calculating or estimating the distribution of a statistic based on one sample.
I like that characterization. Bootstrap is a method of estimating the distribution of a statistic based on a single sample.
Right.
Sounds good to me.
Okay, and the question is, I don't know much about it, but there's something called jackknife. Is that solving the same problem? And another question is this the best method for this kind of estimation? Is Bootstrap? And the third question is, what if our samples are dependent somehow? Is there a variant of Bootstrap which would solve that problem?
Okay. In reverse order. Yeah, there are variants of Bootstrap, but I think they're very specific to the dependence. Next previous question was, is this the best method for doing what we're describing? It's the best method that I know of. It's the best method that, yeah. So it's the best method that I'm here to tell you about. Yeah, Bootstrap was a big deal invention. It prior to this, jackknife was indeed another technique to the same thing. I'm trying to remember what that was about. Anyway, but the Bootstrap is kind of basically superseded the jackknife. No one really uses jackknife anymore. It shows up on problem sets now and then just because you can, but. Was there another question also?
No.
Okay.
I was just wondering if you could keep like 2n or something, like you take however many samples from your data set as you want because you're doing replacement. Is that just repetitive information that's not going to improve our?
Okay, very interesting. Okay. So what if you're saying you drew a sample size 2n,
Mm-hmm.
and what would the idea be again?
Well, so if we're just following this, then you could have a smaller, a more narrow distribution, but you're still just using the same data that you already have.
Okay. All right, so I think what you're getting at is, well, if we want to pretend that this Bootstrap sample is as good as an original sample, well, why don't we get tricky, and we're trying to get a really good estimator, why not just take a sample of size 2n or 10n, and then won't we just have a better estimate?
In that case, you can't take sigma where xi inside the solution because xi will be correlated.
Because?
Xi will be correlated. I mean,
Okay, so, but the assumption, the leap of faith here is that we are kind of treating a Bootstrap sample as though it's a real IID sample from the original distribution. I'm saying that acting in that way gives you results that make sense for things like variance estimating. But the same stuff doesn't go through for that kind of thing. So, which is good, because that would be crazy. Right? All right, any more? Yeah. Sure. Okay, so the question is, if you knew your data was noisy, which I'm going to take to mean high variance, or what?
Yeah, high or like you knew that maybe some of the data points were like
Outliers or something. Okay, and then the idea is are you hoping to get some robustness by taking a smaller sample?
That even less likely those outliers.
Okay, so that's interesting. So, so first of all, that is along the lines of let's just make a new estimator, whereas the motivation for the Bootstrap is let's figure out the variance of a given estimator. So the estimator is I'm going to compute this function on a data set of size n, and now I want to use Bootstrap to figure out the variance of that estimator. And now you're suggesting, let me suggest a new way to estimate something by subsampling something smaller than n and computing my thing on smaller than n, because maybe then I'll get luckier and avoid the outliers or something. Okay, so I don't know, the limit of that approach is like just take something of size really small. So there's obviously a trade-off, right, between using all your data, which might have some noisy things in there, versus a smaller subset of data, which is just giving you less to work with. So I don't know, I don't think that would help, but maybe there are some strange distributions out there where it actually, I mean, there are distributions, which is crazy. There are distributions where if you take a bunch of samples, if you take a sample from the distribution and you average those points, your estimate of the mean of the expected value of the distribution is actually worse than if you took a single point as your estimate of the expected value of the distribution. So there is a crazy distribution where what you're saying is actually the correct solution. Like, don't take endpoints. The more you have, the more you're going to get messed up by outliers. Just take one. But that is a very unusual scenario.
Does it have to do with like the size of the sample? Like, where you get
It has to do with the fact that the distribution has very, very heavy tails. So very likely to get a very large number. Like there are distributions that don't have variances, and there are distributions that don't have expectations. So the Cauchy distribution is what has a lot of these strange properties. Okay. Yeah.
So we have the assumption about the distribution of the sample, like should it be Gaussian or
No. No, this is no distribution, no assumptions on the distribution. Yeah.
Related to that question, you mentioned that the math is heavy, but are there any red flags we should be aware of before applying Bootstrap? Or like, once we apply it, are there any sanity checks we should do to make sure it is giving us a reasonable distribution?
That's a nice question. Not that I'm aware of. So I think I can get back to you on that though. I could look into that. But nothing enough that that stand out. So maybe the theory will have some. Well, I don't know. Okay. All right. So far we've talked about Bootstrap. Now we're going to talk about why you might want to do something like averaging your Bootstrap samples. Okay, but let's sidestep into that. All right, so let's start with a scenario and do what we're calling a lousy or a bad estimator. Suppose we're starting over now, okay? We have z's 1 through n, they're IID from some distribution, they have expected value mu and standard and variance sigma squared. Okay. We want to estimate mu. So one particularly poor estimator of mu would be z1. What happens with z1? What's the expectation of z1? Is? The expectation of z1 is mu. So it's an unbiased estimator of mu. That's a good start. What's the variance of z1? Sigma squared. The variance of z1 is sigma squared. Okay, so we could use z1 to estimate mu. We're leaving a lot of data on the table, but it's an estimator. And so the variance is sigma squared, and the point is we can do better than sigma squared by averaging. So the average, if we take the average of z1 through zn, well, actually this is a calculation we just did over there. It has the same mean, mu, good, but now the variance has gone down by a factor of n. So standard deviation has gone down by a factor of square root of n. So this is in a nutshell why we take averages, because the variance goes down by 1 over square root of n. Okay. All right, so the question is, can we use this phenomenon to help us with, machine learning? So this is very simple parameter point estimator. Can we use this to help us with machine learning, where we have prediction functions and that sort of thing? So let's go back to our original idea. Let's suppose we had B independent training sets now, right? from the same distribution. And we have a learning algorithm that gives us B decision functions. So now we have F1 hat all the way to FB hat. Is it clear? We have one decision function based on training our algorithm on each of B different training sets, sampled from the same distribution. Great. So then what would we want to, suppose this is regression. What would you want to do with the F hats? Yeah, I would want to average these F hats. Right? So the average prediction function in a regression setting would be just take the average of the F hats that we got from each of these individual sets. And then you'd expect the variance of F hat to be less than the variance of a single prediction function. All right, just as a concept check, what's random here? So what's random in this description? Training sets are random, exactly. All right, that X there, this is just to indicate that we have functions. It's not random. It could be, but in this setting, we're not saying X is random. All right. So the average, so we're going to fix some X. The average prediction function is defined like that. And then because X is fixed, and we can think of each of these F average of X, that's a number, right? The function is mapping into reals. So this is a random variable, right? It's random because it's random. It's a random training set. So we have a random variable on the left, and we have this average of random variables on the right. So this is pretty much exactly the scenario we were in the first set of slides, where we had these estimators, mu hat, and we calculated them on independent data sets. We had independent random variables. So now we have, again, independent random variables, which is the prediction of the decision functions on a fixed X. Great, so we would expect that the variance of F hat average for a particular X to go down also, like what? 1 over square root of B in this case. Okay. Good. Okay, let's take a few more minutes before a break. All right, so this seems great. We have this, we can take a bunch of data sets and average them, and we decrease the variance, and the expected value is the same, just like before. So it seems like a win, but of course we don't actually, we're back to the same trade-off we discussed before of you have this, really you have one training set, and what do you do if you want the variance? Do you break it up into pieces and average them, but then each of your pieces is much smaller? So what do we do because we don't have the B independent training sets? And now we have a possible answer. Yeah, exactly. So we can, instead of hypothesizing that we have B independent training sets, let's give a try to taking B Bootstrap training sets and training on each of these, and then averaging those. OK. Let's take a break. See you in 10. What's going on?
So awesome.
All right. Rolling? OK. So the idea that we just talked about was, boy, wouldn't it be nice if we had B independent training sets. We computed our decision function on each of them. We combined them, say, by averaging in the regression case. You'd have lower variance, same expected value. That sounds great, but we don't have these replicated data sets. What the heck? Let's try Bootstrap replicates and train on each of those and then average those. So that method has a name. It's called bagging. So let's break that down more precisely. So let's start with B Bootstrap replicates from the original data set D. All of the same size. I left off the subscript. And let F1 hat through F hat B be the actual decision functions based on training on each of those Bootstrap training sets. And then we have something called the bagged decision function, which is basically take all these things and combine them somehow into something we'll call this should be bagged, not average. It's something we'll call the bagged estimator. Let's think about how we could combine these things. So here's some cases. How would we plausibly combine them for regression? Average, yes, great, makes sense. What about for binary class predictions? So say each f hat gives a 0 or a 1. What might you do then?
Average.
Majority certainly makes sense to me. A certain type of average, called a mode, would do it. All right, what if the predictions are probabilities? Average seems plausible. Some way to numerically combine. How about multi-class hard predictions? Yeah, or plurality, whichever has the most votes. Yeah.
Would we be able to average the weights that we take out from the...
Okay, so the question is, do you want to, so I'm suggesting combine the predictions. And you're suggesting, well, what about combining the weights? The actual internals of the prediction functions themselves, should we combine those? That's interesting. So something like that sometimes happens when you do parallel computations, parallel learning. But that would be a totally different approach. Yeah. Well, at least conceptually, it's a totally different approach. In certain situations, it might turn out to be the same.
Regression, for example, would be the same.
For? Yeah, for linear methods. Seems like it for linear regression. Okay. All right, good. So you have some ideas on how to combine. All these things sound good. This is a method from '96. Leo Breiman, a famous statistician who did a lot of machine learning, did a lot of the bridging the gap between statistics and machine learning, was this Leo Breiman guy. He also invented random forests. Pretty much owns this lecture today. He didn't invent the bootstrap. That was a guy at Stanford. Yeah?
In this situation, is there any way to distinguish between the functions and do a weighted average based on how well they predict?
Well, that's a really interesting question.
Or does that not really work here?
No, so the question is, would it make sense to do some kind of a weighted average based on some estimate of how well the f hats did, right?
Yeah.
So I like the intuition. Do you have an idea on how you might estimate how the f hats are doing?
That's what I was kind of wondering, because we haven't really it's more theoretical, so we haven't really said that.
Yeah, well, so you might, okay, so one way that could work is if you had a ton of data, you can estimate each f hat's performance on some holdout data. But we never really have that much. And you can't really use the training performance, at least not in an obvious way, because it depends on the situation, but often f hats are going to be maybe overfit to the training data. So how they do on the training data may or may not be a very good indication of how they do on new data.
Could you combine cross-validation with the bootstrapping technique?
And the goal being to find out weights for the f hats?
Yeah.
That's interesting. I think the closest that we're going to come to that is the next topic, which is boosting, out of boost, which does definitely have a flavor of this combining by how good the prediction functions are. Cool. Okay, so let's talk about regression, bagging for regression for a minute. So here, I got the subscript right. So here the bagging is, yes, the average of the predictions of the regression functions. And so if the bootstrap samples are actually independent draws, so not bootstrap, but the real thing, independent draws from original distribution, then f hat bag would have the same expectation of any individual decision function, great, and it would have smaller variance, which is very nice. So empirically, one often gets a similar effect for bagging, but sometimes there's no effect and sometimes there's a huge benefit of bagging. So, and why? Well, bootstrap samples aren't independent samples from the original distribution. They're bootstrap samples. So there's no guarantee it's going to help, but sometimes it does help. And I'll give a little bit more intuition in a slide on when it might, or when people say it might. There's one cool thing you can do with bagging. So remember, every time we took a bootstrap sample, something like 37% of the data set is not included in the bootstrap sample, right? Okay, so if we train on the 63% that we're left with, we could predict on the 37%, and that would be an out-of-sample prediction for that particular decision function. So there's kind of a built-in test set for any given decision function that we train on a Bootstrap sample. Is that clear? Right, whatever's still in the bucket after we draw our Bootstrap sample, well, we didn't train on that for this particular decision function, so we could use that to get an estimate of performance. But so let's extend that idea a bit. So let's now look at each of the n training points. So we're going to let S sub I be a set referring to the ith training point out of n. And we're going to let B be the indices of all the Bootstrap samples that do not contain the ith training point. All right? So we got capital B Bootstrap training sets, and roughly 37% of them are not going to have the ith data point. Let's collect those. Let's collect the prediction functions f hat I. Let's collect the prediction functions corresponding to the data sets that did not train on that data point. And let's evaluate the prediction performance by how it does. Next slide. All right. So we call it the out-of-bag error estimator, or the out-of-bag prediction function. Basically, we're going to predict on xi, the ith training point, to get an estimate of how well we would do in an out-of-sample sense on xi. We look at all of the f hat b's that were not trained on the ith data point, and we average the predictions of those functions. So f hat OOB, we can look at how it predicts on xi, and the performance on that data point is somehow a legitimate out-of-sample performance. Any questions on that? Is that clear at all? Some people found it clear. Yeah. Say again?
This could be used as an estimator for the weighted average, as you mentioned.
Yeah, I guess I could. That's interesting. Let's think about that. Yeah. All right. Does anyone have a question to ask on this? All right. All right, so this is a pretty good way to estimate test error. It's kind of just a side benefit of using this type of method. In practice, it's if you have the data, it's better to use a validation set. It's more accurate, typically. But okay. All right, so here's an illustration of what happens when you bag trees. How are we going to bag, say, classification trees? So we discussed two methods already. It's a classification, so you could either do a majority or a plurality vote of the classes, or you could average the probabilities that are predicted. All right, so here's 5 different trees so we have a sample size 30, and then we built a tree on that, and we get this original tree on the top left. And now we took 5 Bootstrap samples, also of size 30, and built decision trees on each of those. And we got 5 more decision trees. And what's interesting is that the decision trees are often quite different. So the structures are different. Can you guys see these variables? The first variable here splits on x1, x2, x2, x3, x4. They're splitting on a different variable in the root node. The trees are quite different in how they're doing the classification based on the different Bootstrap samples. And this kind of instability to changes in the data set, some mild changes in the data set, that is often referred to as kind of high variance. It's a high variance method that a small change in the training set can lead to large changes in the final prediction function, or at least the structure of it. Okay. And what we'll point out later is that people often say methods like bagging work best when you have this kind of, any given tree has a lot of variance to it, a lot of variability, and bagging helps reduce that variability. All right, so here's a picture of bagging trees using two different methods. So every tree, of course, you have very easily either probability prediction or a hard class prediction based on the relative proportion of classes in your leaf nodes. And so on the x-axis, we have the number of Bootstrap samples that we're using, that we're averaging together to get our bagging estimator. So all the way on the left, we have 1, right? So we have a single sample from the original. And then as we take more, the test error, so this is the performance of the average of B Bootstrap samples, it decreases very nicely initially, and then it kind of levels off, which kind of makes sense. There's only so much error that's due to the fact that there's some randomness in your data set. More of the error is the fact that you have a small data set, I would say. All right, so eventually you kind of max out how much benefit you can get from this Bootstrap resampling. And kind of can see there's not too much difference between the consensus method, which is the yellow, and the probability method, which is green. Any questions on this or the previous slide?
Is it that probability combining method is more robust?
Yeah, this picture maybe seems that probability is a little bit more robust. It varies from situation to situation, so it's probably best to try them both and do some cross-validation or something. Yeah. Sorry? What is consensus? That's another word for like majority or plurality, or whichever has the highest number of votes. Consensus really means everyone agrees, so that's not really a consensus, but because the rest of the story is the one who were the plurality that convinced the rest of the people to agree with them, and then it was consensus. So. All right. So a lot of times so bias and variance have a technical, there's one definition that everyone agrees on, which is the one I've given you, which is the case of you're predicting a real value, and you have your expectation and your variance, and that whole story, that's not disputed. But people would like to use the terms bias and variance in broader scenarios where you're talking about classification, not regression. So I want to give you a flavor of what people have in mind when they're saying bias and variance in those scenarios. And it's kind of related to estimation error and approximation error, but I'll treat them separately here. So, all right. So we have a hypothesis space. We always have a hypothesis space. Let's call it F. So just introducing the hypothesis space, we'll use the term, it biases the fit, which is to say, it's a bias on the fit you end up with because, well, it has to come from that hypothesis space. It's a restriction. A bias in this scenario is like a restriction of this prediction functions you could come up with. Someone comes in and says, I want to use a different hypothesis space. OK, you've just biased things differently. When you have a big hypothesis space, that's one level of bias. And if you make it strictly smaller, that would be maybe more biased. OK, I just want to get you comfortable with this usage of the term bias. You could say you bias towards a simple model. Yeah. You can bias also, in some sense, is pulling you away from the best possible fit of the training data, right? That's kind of the idea of preventing overfitting. You could perhaps fit the data perfectly with an unbiased estimator, but you're worried about overfitting, so you pull that estimate away. You bias it away towards something that you think a priori is more likely to be good, like something with small weights or small L2 norm or small L1 norm, or a tree that's not too deep. These are different biases. All right, is that kind of clear? All right. So full unpruned decision trees where you build them all the way out until every leaf node has like one element in it. People generally would say that's pretty unbiased. What would the bias left be in the prediction functions that come out of decision trees that are built as far as deeply as you can build them? Yeah?
Well, wouldn't it basically like memorize the data, so it would be like unbiased pretty much?
Trees certainly memorize the data. In terms of the prediction function that results It's going to go through every data point, unless there's overlap, like two exactly the same inputs have different outputs, but let's get rid of that case. So if every input has different output, then it should hit everything, yeah?
It's not from a continuous distribution, so your leaf nodes are going to be like jagged.
Great, great. So the bias that's left in a decision tree is that the final prediction function is piecewise constant. In every leaf node, it's predicting a constant number, and that's it. That's the character. That's more or less the characterization of maybe exactly where the boundaries of these rectangles are. That, based on the algorithm, that would have some amount of bias, but that's the flavor of the bias. We're biasing towards functions that are piecewise constant, as opposed to, maybe if we did a kernel method, we could fit things exactly, but it'd be smooth. It'd be sums of Gaussian kernel functions or something. Okay. So when we prune a decision tree, we're introducing bias. The bias is you can't have too much complexity. You can only go to a certain depth. You can only have a certain number of leaf nodes or something. All right. So now variance. What do people mean when they're saying variance in this more general setting? So it could describe how much the fit changes as you take different random training sets. That would be one way to characterize variance. So the trees we were looking at, those have a lot of variance in this sense, because a different bootstrap sample can change the tree quite a bit, whereas linear regression doesn't change much when you do a bootstrap sample. So bootstrapping linear regression, bagging linear regression doesn't really do too much. Okay. All right. So conventional wisdom about when bagging helps. And I've gone to conventional wisdom here because I cannot find any hard theorems on this subject. So if anyone comes across some theory, I'd love to hear about it. But the general sentiment is that, so bagging does nothing to eliminate bias. That's fine. The whole point of bagging is to reduce the variance. So bagging helps most when we have relatively unbiased base predictions. So something like a tree, which is unbiased. Linear regression would be very biased. And high variance. When things are high variance, they have a lot of variability. That stands to be helped the most by bagging, which reduces the variability. So is this true or not? I don't know. But I think where people are getting this from is that bagging works well for trees. So trees have high variance and low bias. So that would be like at least one data point to support this general sentiment that you see printed a lot. So try it out. Your mileage can vary. Yeah?
So I'm thinking that you would want to choose B so that you're touching every data point like maybe a handful of times, and you have a limited amount of computation. But is there other considerations when choosing B?
It's not clear to me that it's important to choose B so large that you are very likely to hit every data point. I think there are rules of thumb on B. B is 100 is a common rule of thumb. Some people say 50, and then others say, 100 is better. There, that's the rule of thumb. Okay. It's very empirically based. All right. So any questions on bagging? All right, so now we're going to talk about random forest, which is actually a pretty minor variation, but it's an important variation. It has excellent performance in practice. So let's recall the motivating principle of bagging. It came from pretending we had these IID samples, these IID training sets from the original data distribution. And of course, bootstraps are not independent, right? Bootstrap samples are not independent. So there may be some issue there, right? So it may limit the amount of reduction in variance that we get. So for example, suppose all the bootstrap samples were exactly the same, right? This won't happen in practice, but imagine you just repeated the exact same data set every time. well, then obviously all the f hats are exactly the same. So averaging them does nothing. So that's the limiting case of identical Bootstrap data sets. Bagging gives you nothing. OK, good. So maybe there's something we could do to reduce the variance, to reduce the relation, the correlation, the dependence between the different Bootstrap samples. So that's kind of what we're trying to do with random forests. But let's first rehearse this math result to make it concrete. So we have, suppose you have n IID random variables. We've looked at this several times. The variance goes down like square 1 over n, variance of the average. What happens if we say the zi's are correlated pairwise? OK. So you can actually have a similar result. So what if the z's are correlated? So suppose for all pairs of zi and zj, their correlation is rho. Then the variance of the average is this expression. Suppose rho is 1. They're perfectly correlated. What happens on the right? Rho is 1. This second thing goes to 0. So the variance is sigma squared. That's back where we were when you only had one example. What's the other extreme? No correlation. Rho is 0. OK, this thing drops, and then we get 1 over n sigma squared, which is what we're hoping for independence. That's what we got from independence. So as the correlation changes, you get this sliding between, this trade-off between sigma squared and sigma squared over n. So this is our math motivation to try to decorrelate, to try to get each of the fi's to be as uncorrelated as possible. All right. OK, so here's what a random forest is. Random forest is you take this bagged decision trees. So you're using decision trees, and you're doing your Bootstrap replicates, and you're bagging them, so combining them in some way. But you're going to modify the way we grow the trees. All right, so we're actually going inside this tree algorithm, and we're changing it a little bit. So the key step in random forests is that when we're building the tree, and we are at a node, and we need to choose a splitting variable in the split point, the choice of splitting variable is restricted by first choosing a random subset of variables, random subset of features of a certain fixed size, but not the whole set. So maybe a typical amount would be if you have d features, at each node we choose a random subset of square root d features. So if there's like 100 features, then at any given node we pick 10 of them randomly, and then we choose the best variable from those 10. And then when we go to left, we do another different random subset of size 10 from the 100 features, and we split on one of those. And the idea, everything else is unchanged. So the idea is that now we're introducing a fair bit of, diversity in our trees, because it's, first of all, even the very first root node, which is very important in the eventual tree structure, it's pretty unlikely to overlap with a square root of d feature sample to choose from. All right, so that's pretty much all there is to say about the random forest algorithm. We can talk about it a bit, but that defines it. So square root of p, if p is the number of features, is typical. But it's worth trying other things like p over 2. You could be more aggressive, be less aggressive on this. And then you could choose what fraction you want to use based on cross-validation, as usual, something like that. Yeah?
But you bootstrap the sample as well?
Say again?
You bootstrap the sample as well, or you only change the...
Yes, you bootstrap the sample as well. So let's act it out from the top. Here's the full data set. OK. Draw our first bootstrap sample. Now we build a tree. Choose square root of p features to decide on the root node, and so on. And then we build this whole tree. Another thing I didn't mention is in random forest, you typically build the trees very deep. So until every node has maybe 5 data points in it or something, a deep tree. What happens to the deep tree in terms of bias and variance? Very low bias, that's right. Yeah, and we're getting even more variability than usual in our trees because we're doing this random feature selection. So we've just bumped up the variance a lot, and by building deep trees, we're doing low bias. OK. So we build this whole tree out, a deep tree. Done with that tree, now we take a new bootstrap sample and repeat the process. Yeah. And then we, say again?
And then you bug.
And then you get a whole bunch of trees. 1,000 would not be unusual. Trees, and then you combine them in some way. Yeah.
You had said, here it says to restrict the set of variables when you're choosing a node. Does it make a difference in practice if you were to just restrict the set of variables for each bootstrap sample?
So the question,
All the nodes in the tree?
yeah, so can we use a variant of this algorithm where we fix at the beginning of each tree a subset, say of a certain size, 10, and then we have to build a whole tree using just those 10 features and not the full 100. So that's a new variant. So, okay, you invented a new algorithm. So the question is, does it work? Does it have intuition? Do we have intuition that it would be better or worse? I'm not sure. You could try it. What are the implications? Any given tree will not be very powerful, right? Because any given tree only has access to 10 features in this case, when there's really 100. So you're limiting. So in terms of bias and variance, what happens with this method?
Increase the bias?
Increase the bias, because we're saying whatever function you come up with has to depend on only 10 features. So in some sense, that's biasing towards functions that have a limited dependence on the feature set. So I wouldn't put my money on it, but I'm not saying it's, it could be worth a try. Yeah.
How exactly do you combine the different trees?
Well, trees are the trees we're talking about are classifiers. It's not a matter that they're trees or not. It's a matter of what they produce, because we combine what they produce as functions, as prediction functions, and not their internal structure. So, how would you combine classes? Majority, yeah. How would you combine probabilities? Average. Yeah. What about SVMs? What do SVMs produce? There's a hard decision, but there's also a score, a number. Yeah. Okay, so there's a question? You guys can think about that. Yeah.
So these are like very sensitive to data, right? So this correlation are huge problem. Like because for each bootstrap, the variance will be high. So ideally your tree should be different for each.
Okay, so.
I just want to know if correlation is a huge problem, like in the case of.
Oh, okay. It's hard to know. And this is mostly intuitive. So you're asking, because of all the argument we've done about trees being unstable and being variable, is there really any issue with correlation for trees? Let's just say that it works well for trees. So in some sense, that it can't be such a big issue. There's no theorem here anywhere. So in some sense, this is all intuition and try it and see how it works. And the reason you're hearing about this today is because this works. Yeah.
Would there be a situation where you would prefer to use bugging in trees instead of random forest?
Is there a situation where is there any situation where you would just do bagged trees instead of random forest? In practice, I would say no. This is not a theorem, but this is a practical empirical observation that you should use random forest. Yeah. Yeah. Maybe you don't. Yeah. Okay. So there may be practical reasons to do bagged trees, but as far as performance, I'm not sure. Yeah.
Is there any, other than just observation, reason why square root of p is a good choice? Is there any reason behind that?
I don't have an intuition. I would say that it's no. To me, it's a category of a lot less than the number of features. So as opposed to like p over 2, which would be another category. And it seems that square root of p works better. I'm not saying there isn't a better intuition, I don't have it. It's a good question. All right. So here's some examples. So empirical results, right? So we're looking at 3 different subsample rates. We have P. So with m equals P, is this just bagged trees if our sample size is the same? If the number of features we're considering at every node is the full set, is this just bagged trees? Yes, OK, it is. So P over 2, and square root of P. And then the performance curves based on the number of trees that we're averaging. First of all, let's just look at the general trend. Just like we saw with bagging, there's a big decrease initially, and then it kind of levels off in terms of the number of trees. What else? Square root of P wins in this picture. See, proof. OK. All right, that's all I had to say about random forest. Yeah, the movie, but it's 500 megabytes and it never finished downloading, so sorry.
Question about this plot. So the worst case probability is worse than 50%. So those trees must have been really bad. Must be in a really overfit case.
That's a great question.
So are we saying that we're actually combining a lot of trees that can potentially be overfitting and we're still getting the results?
Great observation. So we're looking at number of trees. When it goes really small, it goes over a half for at least some of these. So first of all, does this make any sense based on how I described random forest? So you'll see that all the way on the left, we have errors that are over 50%, which for binary classification seems crazy. You should never have over 50% error. And if you do, you overfit your training. This is test error. So if you're getting more than 50%, it sounds like you really overfit your training data. So there's one piece that is not in the official spec of random forest, but is how it's implemented generally, which is that you build very deep trees, which tend to overfit, certainly. So with very few trees, you're going to be averaging things that are overfit, and you're still going to be overfitting. But yes, when you average enough of them, these trees that individually may be overfitting the data, the combination does quite well. Yes. So the next thing we're going to look at is boosting, where we're combining trees that are the opposite, very simple, very small, very few number of leaf nodes. But in random forest, we're combining very deep trees, which may well overfit. I guess I would probably do the same for bagging of trees. Yeah?
Did you say that 100 is the magic number?
A lot of people recommend 100 for bagging. So random forest may have more fun going on as you do. I usually do more than 100 trees for random forest. But it actually is not far off here, is it? Is that what you're pointing out, that it agrees with 100? Another proof. Yeah.
Is the depth consistent across the trees?
There's different ways to terminate your tree building in random forest. So sometimes you could do it with every leaf node has a certain number of elements at most. Different ways to do it. You could do a certain depth.
But you may not have the same level of depth.
No, you should. I mean, you'll have the same termination condition for all trees. Yeah. Which leads us to another great point about random forest is that, I don't know if you guys, well, for the computer scientists here, you should see one thing that's great about random forests from an implementation perspective. Yeah. All right, so there might be some speed up because you're looking at fewer features each time. OK, maybe, but that's very detailed level, and there's actually a little bit higher level thing that can go on here. Yeah.
Embarrassingly parallel?
Yeah, embarrassingly parallel in the sense that you can build all 500 trees at the same time if you have 500 processors. There's no dependence between the trees, so it's very parallelizable. All right. So that's a yeah.
Can you regularize the random forest in some way?
Can I?
Can you regularize?
OK, great question. How can we regularize the random forest?
Is that just trimming it back?
Say again?
Is that just trimming it back after you make
So one way would be to regularize your individual trees by trimming them, or other ways to constrain the complexity of a tree. Sure, that would be a way. Yeah.
I was thinking, like, if you're choosing from M, one particular feature, when it's in a set of M, is never chosen, and you start dropping those features. Would be
So in the unlikely event that a feature is never randomly chosen, and then it kind of
well, not that it's never randomly chosen. It's never after being randomly chosen. It's never chosen.
as to split on.
Yes.
Okay. So what's the question?
Oh no, I was saying, would that be a way of regular law?
But you're not controlling that. That's just the algorithm not doing it, right?
Well, I was thinking that if that's the way of not counting features, of removing features, that's equivalent.
Oh, okay. So you're maybe saying, okay, you're saying as a byproduct of the way these things are built, we may end up not including a feature in any tree, and that in some sense the feature's out of there, and that's feature elimination is kind of a regularization. Okay. Usually the regularization is something imposed on top of the method, though. Yeah. So. No. I mean, yes, there are methods, but I think. Well, what's another? The one parameter here is the M, right? So the regularization for M is clear, right? The smaller M is, the more restricted, in some sense, you're. Well, there's a trade-off, isn't there, between if you're willing to wait long enough in terms of the number of trees, no matter how small M is, you can always get any tree, just as long as you're lucky at every single split node. So there's some trade-off between the number of trees you have and M. All right, I think so you can still ask questions on random forest, but I think yeah, go ahead. Question, random forest? Stretch. No? Sure. Okay. Let's start with boosting, which is pretty neat, and then we'll finish it up next time.
One question. Just
Yeah.
To clarify. So random forest also has like no theory, just like that.
Can you say it again?
Random forest also has no theory backing, just like that.
No. There is some theory for random forest. Yeah, the theory is based on kind of nearest neighbor type stuff. This is the extent of my intuition on it. But there may be theory on boosting, but it's not. Rather on bagging, but it's not as. It's not a flavor of like, oh, bigger variance, bias, that sort of stuff. Okay.
Why do you have deep trees for random?
That's a good question. Why do we have deep trees for random forest? Okay, small bias. So the intuition, should you choose to believe it, is that bagging, which random forest is an instance of, works best when you have individual prediction functions that have low bias, which is, you should think like, fits the data really well, and potentially high variance, so a lot of variability. So the deep trees is the low bias. Fitting the data really well is the low bias. So deep trees, yeah.
Don't you also kind of need it because you're restricting M? Like, wouldn't you not get very good predictors? Like, you'd have, as we said, I think earlier, we'd have high bias if we didn't have deep trees,
Yeah.
especially because we're restricting.
Especially because of the subsampling. Yes, especially. All right. Any more burning questions? Okay. All right. So let's get an intro to boosting, which is a distinct technique and pretty interesting. So it comes into so I mentioned at the beginning we're talking about ensemble methods today, and there's two broad classes. There's parallel and there's sequential ensemble. Now, so the parallel ensemble methods, that's what we've talked about so far today. It's where each model is built independently. So bagging, we built B B models, then we combine them somehow. Random forest, same way. All right. The other one is sequential. So in a sequential ensemble, the models are built sequentially. We build the first model, and then we see how it does. And then we try to build a new model that repairs the failures of the first model, right? So we build a model, and then we see, well, this model didn't do so well over here and over here. Let's build a new model that tries to do well exactly in those places. And then we keep building more models to kind of tune things closer to the ideal. And that's what boosting is an example of. So boosting, there's this classic question in statistical learning theory, in machine learning. It's called the boosting question. And the question was this. Suppose you have something that's called a weak learner, which is a classifier, on the classification case here, that does slightly better than random guessing. So if it's binary, we have a classifier that can beat 50% correct. It's a pretty light requirement. So there's kind of like rules of thumb. So you could say, all right, email from a friend is probably not spam. A linear decision boundary, it's a very simple prediction function. It may not be very accurate, but it's a rule of thumb. It may beat 50% guessing. So these are examples of weak learners. And the question is, can we combine a set of weak learners to form a single classifier that makes accurate predictions? All right. And this is kind of, it's a formal statement. It's precise. Given a set of classifiers that perform better than 50% accurate, can you combine them to have arbitrarily small error rate? So it's posed by Michael Kearns and Leslie Valiant in the late 80s. And the problem was solved by Rob Shapiri in 1990. And the algorithm that solves it, he called boosting. The first solution wasn't quite so practical, but a follow-on algorithm, just a year or two later, is still used today and works great. It's called AdaBoost. Is there a question? OK. So AdaBoost setting, we're in the classification setting, -1 and 1. And we suppose we have a weak learner. So now, whoops. Sorry. Suppose we have an algorithm for taking some data and producing a classifier that's better than 50% performance. So in practice, what we're typically using are things like decision stumps. A decision stump is a tree with only a root node. All right? So it's like a split of the data on one feature. Or maybe a shallow tree would be another typical weak learner. A linear decision boundary, another typical. So those are typical weak learners. And so AdaBoost is based on a notion of reweighting training examples. So remember I said you take your first classifier, you see where it did poorly, and then you retrain on where the first one did badly? So that's where this comes in. Wherever the first prediction failed, got incorrect results, we upweight those training examples to make it extra more important that in the second round, the classifier tried to get that correctly, and so on. So by reweighting the examples, this is how we sequentially adapt to how our prediction function is doing. So to actually get there, let's define what we mean by training with weights on the examples. So here's a training set. We have W1 through Wn giving weights to the examples. Let's say they're non-negative. So we have the weighted empirical risk. So we have the loss on each example, but we weight it by Wi. We re-normalize by the sum of the weights. And what we need to have is a classification method that can handle weighted examples, that can minimize this empirical risk. And most methods we've discussed can do that. But if you can't, it's OK. Can you think of any trick we could use to, suppose I have a black box learning algorithm. It just takes data sets. It does not take weighted examples. I can only feed it in a data set D. Can you think of any way to kind of rig the system to have it essentially fit a weighted training example? Say again? Yes, replicate the records. That's absolutely the right track. So suppose a particular example has weight 2, and all the rest have weight 1. Repeat that example twice. That's the intuition. Great. So that works just fine if your weights are integer. What if they're like fractional? Still, there's this way to do it. Okay. Some ideas? Linear combination, I don't know. Yeah?
Sample with replacement with proportion to the weight, with the probability of choosing a sample proportional to the weight.
Yeah, sample each example with probability proportional to its weight. Great. So we take all the W's, renormalize them so they sum to 1. Now we have a probability distribution on examples. Draw up a sample according to that probability distribution of some size, I don't know, 2n or whatever. Anyway, this is a way to kind of back into the weighted, minimizing the weighted training error. Great. Okay. All right, so I'll give you a rough sketch of AdaBoost and then maybe call it a day. All right. So we have a training set of n examples. We'll start with all the weights equal to 1. And we repeat in this way. We fit a weak classifier, call it G sub. At the mth step, GM will be the classifier we get. We fit it to the weighted training points, start off with uniform weights. And then we're going to increment the weights on points that GMX misclassifies, as I've said. And you repeat m times. And then at the end, you have m different classifiers, 1 from each round. So how are we going to end up with a single classifier? You could average. Say again?
Combine them with some coefficients.
Yeah, combine them with some coefficients. So the way we're going to combine them is not necessarily obvious. It's part of the algorithm. Okay. So yes, we're going to take this alpha m linear combination of the GMs. Now, GM's output, they're not scores. We're strictly dealing with classifiers that output -1 or 1. Okay. So we're taking linear combinations of -1s and 1s for each x. And then we're taking the sign, the threshold, to get the prediction. All right. So what's missing is, what are these weights? So first of all, the alpha m's are non-negative. And here's a roughly speaking. Alpha m's are larger when GM, so the mth classifier, fits its data, its weighted data well in terms of having small training errors. So this is when you're asking about, can we combine them using weights somehow related to how well they do? This is as close as we're going to get today, which is, let's see how they do on the training data, on the weighted training data. So it seems a little risky to use training data to figure out how good this classifier is, because you can overfit training data. But in boosting, we generally use very weak classifiers. So overfitting in a single GM is not such a big issue. OK. All right. So let's stop there, because it just gets more complicated from here, and we only have a couple minutes left. Any questions on the boosting stuff? Yeah.
Not related to boosting, but
sure. Go ahead.
Tomorrow, are we going to cover any material, or are we just meeting with the advisors?
Tomorrow is just meeting with the advisors.
So if we have Professor Bellis on here,
you don't have to come. If you have an advisor who's not here tomorrow, you have to make a separate appointment. You do not have to come tomorrow.